In this final section of integration, we're going to look at how we can find the area underneath a curve that we are not yet able to integrate. And we will be introduced to a technique known as the trapezium rule. Because clearly these curves do have an area underneath them, we have to use something clever to try and approximate that area. So, if we consider the curve y equals f of x, and we want to find the area between the curve, the x-axis, and the lines x equals a and x equals b. So we are looking for this area here. If we then split this area into lots of equal size strips, say n equal strips, each of these strips will have the same width, h. Now we can find h by considering the difference between b and a, so b minus a, over the number of strips. And we can find the height of the boundaries of each strip by finding the corresponding y values from f of x, because we know what f of x is, we just can't integrate it. It's also worth noting that while we have n equal strips, we have n plus 1 different heights that we're trying to find. So 1, 2, 3, 4, 5, 6 has 1, 2, 3, 4, 5, 6, 7 y values that we will need to find. So, we have these y values. We tend to label them starting at y0 so that our n's can match up. But note that we will have one more y value when you come to using this, then we will have the number of strips. So, we need to figure out how we can estimate the area of each of these strips. We know their height, we know their width. So if we consider them to be trapezia, so each strip is a trapezium, we can then use their heights and their widths to find their area. And using trapeziums, we can find a pretty good approximation to the area under the curve. So then how do we find the area of a trapezium? Well, we have y0 plus y1 over 2 times h. So we want their average height multiplied by their width. So then we can take each of these areas and we can add them together, and this will give us an estimate for the area under the curve. So we'll end up with the area being approximately half h times y0 plus y1 and y1 plus y2 and so on and so forth. And we can note that we'll get two instances of each of the inner values and one instance of the values at each end. So one instance of y0, one instance of yn, but we get two instances of y1, two instances of y2, and so on. So then we can factorize this out, so we get this formula: a half h y0 plus 2 y1 plus y2 plus etc., and then one copy of yn at the end. So we then have this formula which we call the trapezium rule. So the integral of a function y is approximately a half times the h times one copy of y0, one copy of yn, and then two copies of all the intermediate y values. And remember that h is b minus a over the number of strips. Now, fortunately, you don't need to worry about remembering this formula, but because it is in your formula book. However, you do need to know how to use it, and we do have to set up a fairly intricate method to do so. So if we consider how this looks graphically, here we have the curve y equals x squared plus 3, and we've got just 2 strips in this case. Now we can vary the number of strips that we have. So if we increase the number of strips, our estimation gets more accurate. So we really want to have as many strips as possible. If we decrease the number of strips, so if we're down to just say 2 or 3 strips, then we have this extra bit of area here and this extra bit of area here, so we're getting an overestimate of the curve. However, if we consider a different function, like this one, we have negative x cubed plus 10, we have a different situation going on. Again, if we increase the number of strips, we get more and more accurate representation of the area. However, at not very many strips, so just 2 or 3, we can see these gaps. So we have this gap here and this gap over here. So now our estimate for the area underneath the curve is an underestimate. So, depending on the shape of the curve, whether it's concave or convex, at the area that we're looking at, we might have an overestimate, we might have an underestimate. Now, to be able to see what that is, it's easiest to draw a sketch and see and look at what's going on. So, we might get an overestimate, we might get an underestimate, but the more strips we use, the more accurate our estimate is going to be. So let's take a look at an example. In this example, we want to find the area underneath the curve y equals 1 over x. Now, as we saw in C1, we can't actually integrate 1 over x. We need some knowledge from C3 to be able to do so. However, we can use the trapezium rule to find the area underneath it. So, we've been instructed to use 4 strips, and we have been told what our b and a values are, what our limits are. So we have that b is equal to 3, a is equal to 1, and our n is equal to 4, because we have 4 strips. So hence our h is equal to 3 minus 1 over 4, which will give us 2 over 4 is equal to a half. So it's helpful to find h first, because we use this to figure out how much our x values are going to change for each of our, so that we can then compute our y values. So we build a table at this point. So we want 1 row for x values and 1 row for y values. So our first x value is going to be 1, and then we add 1 lot of h, so we get 1.5. We add a second lot of h, we get 2. We add another lot of h, we get 2.5. We add another lot of h, and we get 3. And then we've hit our upper limit. So then, finding our y values, we have 1 over 1 will give us 1. 1 over 1.5 is going to be 1 over 3 over 2 will give us 2/3. We have 1 over 2 will give us a half. We have 1 over 2.5, so that's 1 over 5 over 2, so that gives us 2 over 5. And then we have 1 over 3, which is a third. So then we apply our formula, which is the area is approximately equal to a half h y naught plus 2. In this case, we've only got 4 strips, so I'm going to write down each of the y values. So y1 plus y2 plus y3 plus y4 is equal is our formula. We then want to plug our values into it, so we have a half. Our h happens to also be equal to a half, so we have a half times a half. Our y0 is 1, y1 is equal to 1.5, so 2 over 3, so it's equal to 2/3. Our y2 is equal to 1/2, and our y3 is equal to 2/5. Our y4 is of course then 1/3. We then want to plug this into our calculator. So we get a equals 1 over 4 times 1 plus what comes out as 47 over 15 plus 1/3. This then becomes 67 over 60. So then we have our area underneath the curve y equals 1 over x between 1 and 3, and we are done with this question. Now often in an exam you may be asked to apply the trapezium rule in this fashion, and that will involve a lot of marks, or you may be given a table and be asked to fill in some of the values. It depends on the question. So, if you're happy with that, please have a go at exercise 11e. Do make sure to try some of the questions from this exercise, as the extension doesn't actually contain any questions on the trapezium rule. Only exercise 11e actually contains questions involving the trapezium rule. If you're happy with that and you're feeling confident about the trapezium rule, then you can have a go at the mixed exercise 11f, which will test you on anything in this chapter, except of course the trapezium rule.